Okay, time to get started. So here's where we were last time. So we were talking about this dimensionally weird situation of suppose your domain is not the same dimension as the world that it lives in, right? And so the first example we're seeing is that of a curve, like so. And I've drawn this curve now, you'll notice, in 2 dimensions, but there's no particular reason it couldn't be 3-dimensional. Here, let's make it 3-dimensional real quick. Boom, now it's a curve in 3 dimensions, right? I will probably draw most of my pictures 2-dimensionally, but just, again, note that nothing really changes when you go to 3 dimensions. Okay, all right. So, we talked about what a Riemann sum should look like. This is what you get when you basically do a chop it up, add it up strategy on this domain. And we realize this is not any of our previous kind of Riemann sums, and so we have to give it a new name and a new notation. There's the notation. Here's the name. We call it a scalar line integral. We'll see actually pretty soon today why this scalar qualifier is necessary. Okay, so how to compute these things? Well, we pretty much rip off the idea of change of variables. Take your domain that you don't like. Here it is. There's our domain that we don't like. And we're going to view it as being an image of something else. We're going to view it as being an image, in this case, of an interval on the t-axis. And we like that. That's a good domain because we know how to do integrals on the t-axis. This is the very first kind of integral we ever saw, right? Single variable calculus. So what we're going to do then is copy all the ideas from change of variables, take all the things that we have over here in xy space, related to the curve that define the scalar line integral we're interested in, and just figure out how to rewrite them in terms of t. Effectively then doing a pullback through this function. And quick reminder, what kind of function is this? What kind of function is this that views a curve as an image? Well, we have a pre-existing such notion. That's just a parameterization. All right, so we're effectively then going to be using parameterizations kind of in the same spirit of change of variables, and the minor point of order, technically we wouldn't call it a change of variables, but that's just kind of semantical precedent. It's morally equivalent to change of variables. Okay. And we talked through the details last time of how do you do the various aspects of the pullback, and this is what we ended up with, that if you have a scalar line integral, like so, there's what it pulls back to. And notice everything's in terms of t. It's an integral on the t-axis. Plug and chug at that point. Let's do one. So let's start with an irregular wire. Right, this is the example we kind of were talking through last time. A bent piece of metal, effectively. Irregular in the sense that it's thicker in some places and thinner in some places, or made out of a heavier alloy at the start and a lighter alloy at the end, whatever. And so here's the path that the curve follows. Conveniently, already given, parameterized, right? Could have described the path with an equation or something, but in this case, let's get a win under our belts. Pre-parameterized path. And here's a formula for how density, how mass is distributed across this wire, be it for thickness or, alloy type or whatever. Okay. All right. And now I'm going to actually do a bunch of calculations all at the same time here because I can. Because so much of the various calculations that we're going to do really just kind of depend on the curve. So anyway, let's get going. I'm going to simultaneously compute the mass of this wire, the x and y coordinates of the center of mass of this wire, and the moment of inertia around the x-axis of this wire. And here we go. Let's start with mass. How do you compute mass? Well, chop it up, add it up. Right? Total mass is the sum of a bunch of little pieces of mass, and each little piece of mass is mass per unit length times length. So now this is what I like to call the phase one part of the problem. I'm kind of borrowing the same language that we used back with double integrals and triple integrals. What I call phase one is turning an application question into a Riemann sum. And then there's phase two, which is how do you turn a Riemann sum into something you can actually, turn the crank with, something you can actually crank out with the fundamental theorem of calculus. Phase three is the actual cranking with the fundamental theorem of calculus. Okay, so phase one, turning this into a Riemann sum, done. Mass is integral density ds. Now, let's talk about the centroid, or the center of mass, that is. We have an existing formula for the center of mass. Don't forget that, again, just like it was here, mass is density times length. That's the same, we're using the same interpretation there of density. Okay, and then likewise for the other things we might want to compute. Why don't I zoom out so we can sort of get this all at the same time. Moment of inertia is integral r squared dm. And again, dm density ds. The y coordinate of the centroid, again, pre-existing formula, and again, dm is density times ds. So we have here, you'll notice, now 4 separate scalar line integrals to compute. They're all being done, however, over the same curve. They're computing different things. We're computing centroids and moments of inertia, etc. They're all over the same curve that follows the same parameterization over the same range of values of t, over which density is distributed the same way, right? So there's a lot that's about the computations that follow is going to be exactly the same. Okay, so here we go. Getting started. Let me recover my colors here. Recall, when you have a parameterization, the first coordinate is telling you what x is, and the second is telling you what y is. So now we scroll down to here, and anywhere in our Riemann sums we see an x. Oh, here's one. This x right there. We'll eventually plug in for it, and there it is. X is equal to t. So, boom. X is equal to t. Oh, here's another one. X, t. Right? Likewise for the y's. Here's y is t squared. So here you go. Y, t squared. Right? And then likewise with the other integrals. Y is t squared. Y, t squared. Right? So it's really just kind of a matter of plugging in at this point. And then I guess we do have to deal with the stretching factor, but most of it is just plugging in. Okay, let's talk about the stretching factor. We need to rewrite ds as x prime dt. Note, again, same deal for all 4 of the calculations. Right? What is this x prime? Well, this is a calculation that you can do in advance, kind of knowing you were going to need it, right? If you're doing a scalar line integral, you're going to pull back through the parameterization. You're going to have that stretching factor. So we can do it in advance. Here, I take the derivative of the parameterization, and then here I compute the magnitude to get my stretching factor. And notice that's what we have here. Bam. There's the stretching factor. So, step 1, parameterize. Step 2, pull back. Plug in, basically. And then notice all of these integrals with the various plug-ins, etc., have all turned into single variable integrals. That is a plug and chug, right? Likewise, that single variable integral, single variable integral, single variable integral. How we doing? Everybody all right? All right. Okay. All right, here's another example. Let's suppose, and I think I can zoom back out for in. Suppose we have a property, and So here's your plot of land or whatever. And you're going to put a fence around the perimeter of that property. This is as seen from above. So you have a circular property. You want to put a fence around it. The thing is, for whatever reason, you want the height of the fence to depend on where you are. So at this location, X, Y on the property. Maybe you're trying to build a garden there, so you want the fence lower so that it gets more sun or something. And then maybe your house is over on this side. You want a higher fence for, I don't know, privacy or to block the sun or whatever. So all these things considered, you want the height of the fence to be this function of position. All right? Higher some places, lower other places. What's the area of the fence? Right, the fence is following this curve, and it's tempting to say, well, it's just height times the length of the curve. But the height varies. Right, so you get different amounts of area along different lengths of the curve because of the different heights. Okay, does everybody understand the setup? Okay. All right. By the way, why would I want to compute the area of the fence? Well, you may need to paint it or stain it, and stain costs a lot of money, especially these days. And you don't want to buy too much. You don't want to buy not enough. So it's pretty useful to be able to know how much area you need. So here's the idea. If you focus on now a little piece of the curve, let's look on that little piece of the curve, and here I've actually drawn the actual fence. And these are little pieces of fence like so. All right. If you focus on a differential sized little piece that has length ds, right? And if the fence at that location has height h, then notice the area of this picket, I guess you'd call it, kind of a little differential picket there. That area is just height times width. Right? Area, height times length. And then, of course, I'm going to add up over the entire curve, right? I'm going to, for the entire curve there, compute the little areas and add them all up. And there you go, scalar line integral. Everybody see how that happened? And again, now we just have to kind of largely plug and chug. Now, of course, we do need to know our stretching factor, so I'm going to rewind it a little bit and come back up here. This time we were not given our curve pre-parametrized, so that's a little annoying. I'm going to have to actually take my curve described just in words and figure out how to parameterize it. And of course, we've talked about how to parameterize things quite a bit back in Chapter 1. So this would be a good time to rewind back to there and remind yourselves of the various methods that we have for parameterizing things. This one, conveniently, is one that we probably already remember. I hope you all remember parameterizing the unit circle, conveniently done by this formula right here. Okay. And that said, you take the derivative, like so. Keep in mind the stretching factor is the magnitude of that derivative. Easily computed magnitude. Lucky break, the stretching factor is 1. And so let's just toss that in there. There you go. Right? The stretching factor is known. It's just 1. And so we have now done our differential part of our pullback anyway, ds, written now as in terms of dt. And you just got to plug in all the rest of the stuff, and it's all downhill from here. So, in particular, the height function was given as this function of x and y, given in the statement of the question. X and y were not given. Let's see, I can't quite fit that. Here we go. X and y weren't quite given, but when I parametrized, I determined x and y. X is cosine t. Right? Make sure to keep that in mind. When you make a change of variables function, when you make a parameterization, you are literally writing down formulas for the output variables. And so, anyway. And now it's plain old, boring, single variable integral and plug and chug. How are we doing? Yeah.
So did this get you the surface area for only the outside surface of the fence?
Yeah. And if you're painting, don't forget to double it. Yeah. Yeah. Anybody else? Okay. Oh, you know what? One other thing. Let's see. Where do these bounds come from? These bounds actually come from something implicit in this parameterization. This parameterization does the unit circle, but specifically when you go all the way around, for which purposes this angle T, right, there's T, has to go from 0 to 2 pi. And therefore, these bounds, being as they are values of T, 0 to 2 pi. Is everybody okay with that? All right. Okay. All right. So we're going to consider a new kind of a question now. Yet another new kind of an integral is going to come up unexpectedly. But anyway, here we go. So let's innocently approach this question, not knowing what's going to happen. Suppose I want to compute the amount of work that it takes to follow a path while I'm applying certain forces. And so the first thing you're going to think is, we already know how to compute work. It's force dot displacement. What's the big deal? We talked about this back in chapter 1. So why can't I use this formula? So the complication that I'm going to throw into this is, let's suppose that this force is not constant. If it's not, you see that I've got that demonstrated, represented here in the picture. This vector field representing the forces that I'm applying, not constant. It's different here as opposed to there. This formula up here assumes that the force is a constant. It only works if the force is a constant over the entire displacement. Not so here, so the formula doesn't work. Here's the other complication. This formula assumes that you're going over a straight line path, which you see here we are not. Our path here is all curvy and bendy, not a straight line path. So again, second reason that I can't use this formula. Okay, so here we are again in a situation where we want to compute something, but the fact that stuff isn't constant is messing it up, right? And so what we do, the big idea, one of the cornerstone ideas of integral calculus, is that when you have such a situation where, I want to use an easy formula, but stuff isn't constant, chop it into little pieces. Right? So we're going to do the usual. We've done this before. I'm going to take my entire curve here. I'm going to chop it up into a bunch of little pieces. And then on each little piece, I notice that, on that little piece, it is approximately straight. In the limit, close enough. The vector field describing the forces, it's a little different between there and there, over this very small little distance. It hasn't changed. It takes a while for the vectors to actually change dramatically, so they're approximately constant over that approximately straight little piece. So on that little piece, we're going to compute work with an easy formula, and then we're just going to add it up. So, it looks just like previous examples that we've seen. Right? Everybody with me so far? Okay. Details to come. So I do need to talk, though, at first about there is a complication here that we did not see in any of the previous examples, and that is that there's what I'm going to call an orientation issue. And specifically, when I say I want to compute the work moving along this curve, I mean moving that way, as I have it drawn. And which way you're going matters, right? If you are walking into the wind, that's very different from walking with the wind at your back. If you're walking uphill, that's harder, at least from a physics standpoint, than walking downhill. Not so much with your knees, you'll notice when you get older. But from a physics work standpoint, harder to go up, easier to go down. Not so with painting fences, right? If you're painting a fence, it doesn't really matter if you paint by going clockwise, or excuse, I guess that's counterclockwise, or if you paint by going clockwise, same amount of fence. Doesn't matter, right? Does it matter how, if you're computing how much mass there is on a wire, an irregular wire? Get this to move. Does it matter if you add up one way or the other? Not at all. So what we have here is a qualitatively different circumstance that we're going to have to figure out how to deal with. And the first thing, just to make it clear what we're even asking, right? We're going to define this idea of an oriented curve. Here, let me do it like this. So the curve is just an underlying thing. It's like a road. It just sits there. It has no notion of direction. It's just a bunch of concrete on the ground. Right? That's what a road is, or a curve in this case. An oriented curve is when you say, yeah, and furthermore, though, I want to attach that I think of this curve as going specifically a certain direction. And now when I say moving along this oriented curve, now it's clearly indicated what I mean. When I say oriented curve, I know which way I'm going, and now we have an unambiguous question: how much work does it take to move along this oriented curve? How we doing? That make sense to everybody? All right. Cool. So off we go. Here is a little piece of curve. Let's see here. Do it like this. There's a little piece of curve. Here's my dx vector. Keep in mind my dx vector is my differential of position. I was here. I moved along the curve a little ways. I actually ended up here, but based on what was happening at the beginning, at the starting point, given the direction I was going at the time, et cetera, my linear estimate of change in position is this dx vector. And so there's my displacement. Again, round off errors go away. Here's the force that I'm applying. And work is equal to force dot displacement. So on that little piece, if you want to know how much work did it take to move from there to there, what are these little pieces of work that I'm adding up, in other words? Well, there you go. It's F dot dx. And then we just add those up. All those little pieces of work, we add up over the entire curve. Right, whatever that entire curve is, we add up all the little bitty pieces of work. We have formulas for our little. We have a formula for our little pieces of work. There it is, F dot dx. And here's our new expression. Kind of comes a little bit, I'm going to say unexpectedly, semi-unexpectedly anyway. So I'm going to call this a new Riemann sum. And I didn't write it with sigma notation, right? I'm writing this streamlining the convenience of integral notation. But keep in mind, all integrals are shorthands for Riemann sums, right? So this is a new kind of a Riemann sum because, well, look at it. I mean, this is not ds. Distance is not all that matters here. How far I moved is not the whole story. I need to know which direction did I move. That's relevant to the calculation at hand. This is not a scalar density times a scalar distance. This is a vector integrand and a vector differential. So new thing. And yet it's still a line integral because we're still added up along a curve, right? So we're going to use the same term line integral, but now you see why I felt it necessary back let's see where, here we go. Why I felt it necessary previously when we added up along a curve to put in this prefix scalar line integral because f was a scalar, ds was a scalar. Right, and not so in this story here. My differential, my integrand is a vector. My differential is a vector, and thus the term vector line integral. How we doing? I hope that's satisfying, right? Is everybody okay with that? So, good news, bad news. The good news is we have a new mathematical construction that allows us to answer new kinds of questions. Isn't that nice? Bad news. return to, I don't know how to compute this thing, right? This is, we're going to have to figure out a technique for dealing with this again. So really, it's good news, bad news, good news, though. So, new capabilities, new computational problem, and the final good news is we, in fact, already have everything that we need, believe it or not. In the process of writing down scalar line integrals, everything that we need to compute this, we've already got. In particular, I've got formulas for dx, pre-existing formulas for dx, no problem. Dx is x prime dt. Right? I need to be able to follow the curve, right? Well, yeah, okay, exactly, but that's what parameterizations do, right? So, we're good. We, in fact, even though it's a brand new kind of a Riemann sum, we technically already know how to compute it. And here's the formula that we're going to compute with. Pausing real quick before I go on. Any questions? Yeah.
So, am I just missing the formula stretching factor in this?
That's a great question. Great question. It is here, believe it or not. It's just a question of how it's kind of hidden. And let me rewrite this. Oh, let me do this in a better color. Do this in purple. X prime dt. I'm going to rewrite that as unit tangent vector times the magnitude of x prime dt. Right? So effectively, what I've done here is I have separated out the direction and the magnitude of the velocity vector. So there's your stretching factor. It's right here. It was just kind of hidden inside of the velocity vector. Is that fair? Yeah. Right. Notice then further that this same little rewrite that I did here justifies the next formula that we have for it, because t magnitude of x prime dt, well, magnitude of x prime dt we previously wrote as ds. Right, so that's why these two expressions here are the same. And let me fill in the So x prime dt is the same as capital T ds because both of them are equal to this. And the only difference between these two is that the stretching factor is hidden in different places in these two different notations. So, excellent question. Thank you for that. Does that make sense to everybody? Okay. All right. Let's do one. All right. So, you're walking around on a windy day, and you're in particular going to walk counterclockwise along the top half of the unit circle. Let's real quick draw a picture of that. Here's the top half of the unit circle. And let's see here now. It says specifically that we are walking counterclockwise. Counterclockwise is this way. Like that. Alright, so there's our walking path. As we walk, there is a force that's being applied. And notice the way I have this expressed. Wind is exerting a force on you. There's this awkward thing in physics. It's an annoyance, really, from a math point of view. But whenever there is a force being applied, there's really kind of two forces being applied. So, for example, here I'm holding up my stylus. There are actually two forces in play here. One is gravity is pulling down on my stylus. Right? So there's a downward force of gravity. Yet it doesn't accelerate toward the ground. Because of a second force is the force that my hand is applying. I am applying a force upward. Right? And these oppose each other exactly. Therefore add up to zero. Therefore there's no acceleration. That's which explains how it's just sitting here. Right? So there's always two exactly opposing forces when you have a static circumstance. And so you got to be careful though then which one is the one that you use in the integral. And it all comes down to, well, what are you interested in, right? Are you interested in this little story here with my stylus that I'm holding up? Are you interested in the work that I'm exerting? Or are you interested in the work that gravity may be exerting? Right? So notice that the force that's been given, F, this is the force that the wind is applying. This F here is the force that the wind is applying. The question, though, is I want to know how much work do you exert? And you push with the opposite force, right? You push with the opposite force because, again, you're not falling over. And so there's a minus sign in there. The wind is applying a force F. You, in resistance of that, are applying a force negative F. What do you think? Is that all right with everybody? Okay. All right. So a little physics annoyance. A heads up, by the way, this kind of thing is unavoidable. It's going to be around, and so when you read one of these questions, if ever there is a force involved, you have to look carefully at the way the question is phrased to figure out. Wait a minute. Did they give me the right force or did they give me the wrong force? And if it's the wrong one, you got to stick in a minus sign. Okay. Alrighty. So, let's see. We're interested in the work that you do. You push with force negative F, so there's your integrand negative F. We've already established that work is a vector line integral of force. And so now we just have to punch this up. Step one, of course, got to parameterize. How do I parameterize this curve? Let's see, I guess I could do it like this. This curve, well, again, unit circle. So easy to parameterize. Our old friend, cosine t, sine t. It's even going the correct direction, counterclockwise. Isn't that nice? However, do notice that you're only going halfway around because this is the top half of the unit circle. So we're only going 0 to pi. And then it's all, I didn't mean to erase that. It's all downhill from here. There's the derivative. Magnitude is 1. And dx is x prime dt. Right? X prime previously computed. Right? Let's see here. Negative F. Well, let's be careful with this. F is this given formula that's a function of y and x. Y and x, though, don't forget from our parameterization, y is sine t and x is cosine t. And notice I didn't try to do too much all at once. It's easy to kind of do too much all at once and forget some minus signs. Like in the process, you got this minus sign from the whole opposing force thing, and then you have this minus sign here from the original formula. It'd be easy to kind of accidentally forget one of those, right? So I advise slowly and carefully. Make sure that everything that should be there is represented, and don't try to do too much of this in your head. Easy to mess it up. Okay, is everybody on board? Okay, and then turns out to be an easy integral. This integrand altogether is, by the Pythagorean identity, just 1. And it turns into the world's easiest integral. And there you go. Okay. All right. Okay, now let's go back up here for just a second. I parameterized this curve. This curve had a derivative. Here it is. That derivative, of course, is telling me velocity. But wait a second. Am I actually walking with this velocity? Where in the statement of the question did it say I'm walking at unit speed? It didn't. So am I making stuff up? Is it fair for me to assume that I can just parameterize this curve kind of however I want, and I can walk real fast or I can walk slow and it doesn't make any difference? When you think about it, when you do a mountain climb, yeah, I mean, it really shouldn't matter. I mean, what matters is along each little step. It's not how fast you move. What matters is, well, how much force and how much displacement. Speed shouldn't matter. Right? So, good news. Line integrals don't depend on the parameterization. Except for one little detail. And that is this right here. You have to parameterize the direction of the given orientation. And this is something you really have to pay attention to. If you parameterize it backwards, then you're describing a very importantly different story, right? If you parameterize it backwards, then you're computing the amount of work it takes to go down the mountain path, not up the mountain path, or vice versa. Does that make sense? Okay. Other than that, parameterize however you like. If you do go backwards, of course, if you think about it, all that does is make all your dx's going exactly the wrong way, aka they're exactly the negative of what they should be. And side note, that's every one of your differentials is exactly the negative of what it should be. And so in the total, you will get exactly the negative of your answer. Yes?
What is the orientation look like on the
On this picture here?
Yeah.
Yeah, so orientation, let me come back where I have an existing picture. Orientation, think of as sort of an attached indication of which direction are you going. So that's one orientation. And now the opposite orientation, also an orientation, would just be, I'm going the opposite direction. Yeah. So there's always, for any curve, there's always two possible orientations. And it's just, which way are you going? All right. Okay, so neat fact that we had here, though, that I've kind of talked through. If you parameterize backwards, all you're going to do is just be off by a factor of -1. So here's the theorem. If you and there's a notation introduced in this theorem. This right here, this little superscript of a minus. All that means is go backwards along the given curve. So C is oriented one way, C minus is same curve, just oriented the other way. It's just a notational thing. I'm copying the book's notation here. And if you do that, all that does is introduce a minus sign in the value of the integral. Okay. All right. So there you go. All right. Let's do another example. I'm gonna answer this question 3 different ways. I think all 3 are worth knowing. This is good tools for your toolbox, as it were. And here we go. So we want to look at the same story as the previous example, but this time instead we're going to walk clockwise. And so we aren't going to use the same parameterization because, after all, clockwise means I got to go this way. Right? It's the same road, but it's not the same road trip because I'm going a different direction. Does that make sense to everybody? Okay. All right. Well, I'm going to give you 2 ways to parameterize this new, it's literally a new oriented curve, right? Because it's got a different orientation. So, first way to parameterize it, realize this, let me go to pencil mode. This point here is where I am at t equals 0. And I'm going to move along, let's say, let's keep it simple, unit speed, right? And by the time I get to the end, this is where I am at t equals pi. So that represents this process of going that way. And notice then that this angle is really the angle that represents what t is doing. If I had to draw t on this picture, there it is, it's that angle. And the bad news is that's not the theta angle that we're accustomed to. You know, sine and cosine are defined strictly where angle is measured off the positive part of the x-axis. That's not what this angle is. So I can't just start writing down sines and cosines. What I can do, and this is very convenient, and this is the trick, once you've identified what your natural angle is, the angle that most closely connects to your story, you can then geometrically connect it to the theta angle that you actually need. And notice here, this green angle plus that purple angle, always pi. And so theta, right, the thing whose cosines and sines give me the path that I want, theta is just pi minus t. And so, yeah, cosine theta, sine theta, just make sure to be precise about what theta is and how it relates to the parameter that you actually need to use because of the direction that you're actually going. Is everybody happy? Yes.
Just going back to the velocity thing. So if they told you you're not going unit speed, could you just
ignore that? Yeah, you absolutely ignore it. Yeah, two friends are walking along the rabbit and the hare, are racing along the same trail. And one of them's going faster, one of them's going slower. You decide who, right? Who exerts the most work? Neither. It's exactly the same. Yep. Good question. Anybody else? All right. Okay, different way to parameterize. Now I emphasize this exact same curve. So again, I'm going to, indicate same. Here we have t equals 0. Here we have t equals pi. And so again, we are going clockwise. Different way to think of the parameterization is like this. The path that I want to parameterize, right, the XY formula that I want, is a reflection over the y-axis of this path, which I already know how to parameterize because this is our old friend, the counterclockwise around the unit circle, and so that one I already have. Right? So you can see straight from the picture that the blue parameterization and the green parameterization are literally mirror images of each other. And so all I have to do is think, well, how would I then mirror image? How would I reflect across the y-axis? And you just have to kind of think through the geometry of reflecting across the y-axis, and all that happens is you get a minus sign on the x-coordinate, right? So that minus sign is an immediate consequence of the reflection, and bam, there you go, same result. So also a good little trick for how to parameterize in this case. Again, it's always about cases. You can't memorize a list of this is how you do them. Right? It's tools in your toolbox, and you want to make sure that you're familiar with all your tools. So here's two good tools for parameterizing. Yeah.
Could you explain again why we can't parameterize from t equals 0 to xy? Just like plugging in cosine, like for the first one.
Back in the first one? Okay, give me a second.
Why can't we just do cosine t?
Oh, yeah, because t is this angle. And that's not how sine and cosine work. Sine and cosine are the coordinates of the point that you get when you measure an angle counterclockwise off of the positive part of the x-axis. So this is theta. This is the thing where sine and cosine are x and y. And it's just a strict rule. That's the definition of sine and cosine. Does that make sense? Yeah. So the thing that actually describes the thing that is 0 when time equals 0, the thing that is pi when time is equal to pi, that angle, not the same angle. Yeah. Yep. All right, and then plug and chug, and you get negative pi as an answer. So I promised you 3 solutions to this question. I've given you 2. I owe you one more. The other one is actually extremely satisfying, and that is to just say, oh yeah, well this is the same curve as previous. The only difference is the opposite orientation. Opposite orientation just gives me a minus sign. So boom. It's the minus of what we've already computed, and therefore it's minus pi. That's the good one. That's the easiest solution, because we happen to have already computed the counterclockwise line integral. This one is a freebie. Everybody all right? Okay. So yeah. All right. So here's the next thing to think about. So we've got this brand new construct. Oh, I don't like the red. We've got this brand new construction. This vector line integral. We understand that vector line integrals compute work. Pause. Slow down. Clarify. If the vector field that you're doing a vector line integral of represents forces, then line integrals represent work. Let me take you back now that when we first defined vector fields, there really were two pretty big physical metaphors or physical contexts in which we'd want to talk about vector fields. One of them was forces. It's nice to know that when our vector field represents forces, then line integrals represent work. That's nice. What if, though, in the perfectly reasonable scenario, right, what if your vector field represents a fluid flow? I mean, lots of vector fields represent fluid flows. There's lots of circumstances where I need to represent fluid flows. There's no forces involved in the question at all. I've got fluid flows, and if I have that scenario, vector fields representing fluid flows, now, what does this thing here represent? It's not work. There's no forces involved. The vector field is a velocity. So, what is this thing? Right? And it's not an immediately clear question to answer. Reminder, our line integral, we've got a setup for this. The players involved in this formula are in this picture that relate in these ways. Again, we already talked about those. I just want to have this kind of for convenient reference. And these can be computed by either of these two formulas. In order to answer this question, I'm going to have to kind of start with the answer and work backwards toward my claim that line integrals have something to do with the question that I'm asking. So it's a little bit weird. It's going to kind of seem to come out of nowhere. But I think this is the best way to do this. So let's suppose that you have yourself a curve, and there's a vector field representing a fluid flow. So I don't know, maybe the fluid flow is like something like that, let's just say. Suppose I were to be interested in just the fluid that's kind of near our path. Like that. This kind of thin, sort of like, you might say, in the vicinity of our curve. Right? And if I want to know, okay, we've got this fluid here, and fluid flows, pieces of fluid over here are kind of flowing kind of like that. To some extent, those pieces of fluid are flowing along the curve. To some extent, they're flowing perpendicular to the curve. And let's just suppose, for whatever reason, that I'm interested in knowing the extent to which the fluid is flowing along the curve. All right. So that's the question that we're going to ask. What is the total... Oh, gosh, how to say this? It's awkward to describe in words, but the total, along the entire curve, looking at all nearby pieces of fluid, when you add up all of their, sort of how much is it flowing along the curve, what's that total amount that you get? So kind of a weird question. But let's compute what we get. And here we go. Here's a little piece of fluid, dV. And there is a flow velocity here. That's the velocity the fluid maybe is actually moving. I don't really care about how much the fluid is actually moving. What I want to know is to what extent is it flowing along the curve. Right? I don't care about the extent at which it's flowing perpendicular to the curve. I don't want to know. I just want to know this amount of volume of fluid flowing along the curve by what amount? And I'm going to say that what I'm actually interested in here, the actual, how much of what the question has asked is coming from this little piece of fluid that is moving along the curve by that amount. I'm going to say, well, let's just multiply them together. It's an arbitrary choice of how to describe, what we've got, but this much fluid, that much flowing along the curve, all together we got that. Is that all right? I'm just making that up, right? Okay. So, good news, I know how to compute components. That's a dot product with a unit vector. And I can rewrite this bit of volume here. Let's see, here we go. This little bit of volume I claim is area times ds, because this area there, that cross-sectional area is right there. That's what the area is. And then ds, this little length of a little piece of curve there. Looking at this picture, you can see that this volume is the cross-sectional area times that ds. So I can rewrite dv accordingly. Is that all right? And then we take our dq. Whoops, wrong thing here. Take our dq. We add up over the entire curve. So, again, the curve actually is, I've got to add up over all the pieces of the curve, and you get an integral. And lo and behold, weirdly, what you get for this is, and I've got a mess here I'm going to clean up. We all together get something that directly involves a vector line integral. And keep in mind, our whole goal here was to try to figure out, what does a vector line integral mean when you're talking about fluid flows, right? And so, vector line integrals have come up in relation to the answer to a particular question. So that's what it is. A vector line integral represents, now there's you got this factor of area involved here, which if you'd like you can think of as kind of dividing over here, to put that in the denominator of the left side of the equation if you want. I'm going to say though, per unit area of cross section that you're interested in, right? Line integrals compute for you the total rate of fluid flowing along the curve. So you can think of it that way. You can think of vector line. If you've got a fluid flow, vector line integrals represent the combined extent to which the fluid is flowing along the curve. It's a little bit hand wavy. It's not a quantity that we originally understood to be a natural physical quantity, but here we are. It is now going forward a natural physical quantity because it's what vector line integrals represent. Sorry, I went over time. We are drawing a line there. See you on Monday for the exam, right? Don't forget we have an exam Monday. All right, so y'all have a great weekend. Good luck with studying. See you later.